Hello, welcome to my presentation of Lab 3 on circuits. So in this lab, we are predicting and observing circuit behavior in both series and parallel orientations. This will help us learn more about resistor behavior and capacitor behavior. The necessary materials are two 1.5 volt batteries, alligator clips, multimeters, light bulbs, resistors, and capacitors. And the results we found are that Kirchhoff's circuit laws hold true. So the fundamental principles we need for this lab are two of his laws, the node rule and loop rule, as well as Ohm's law. The node rule basically states that the sum of outgoing currents is equal to the sum of incoming currents through a node. And then the loop rule, which is based on the energy conservation principle, says that starting at any point, going around the full loop in any path, when you get back, the change in voltage will be zero. Now, this just makes sense. But in practice, this means say you go through a battery of 3 volts, you know to return to that same point that you have to have 3 voltage drop throughout the rest of the circuit. Also, we have Ohm's law, which just says that voltage is proportional to the current between 2 points. And then we can calculate things like this with resistance. So in our first setup, we have this circuit in series with a 3 volt battery, 2 resistors, and then ammeters. So we're supposed to predict using Ohm's law the current at each ammeter, which is actually the current anywhere in the circuit. And to do this, we do 3 volts divided by total resistance, which is the resistance of both summed. And for this, we found 20.4 milliamps as the theoretical value for anywhere in the circuit. And our actual was 20.4 and 20.4. So this just shows that anywhere in the circuit, the current is 20.4. And then the question is posed, what happens if we reverse the connection to one of the ammeters? And the result is that nothing changes because the circuit is unchanged. Now, if you replace one of those ammeters with a voltmeter, what happens? Well, voltmeters have nearly infinitely high resistance. So as resistance goes up and the voltage stays at 3, I goes towards 0. Basically, the current is decreasing a ton because of this new resistance. And then the question is, why does a voltmeter read 3 volts when you would expect voltage drop to also be coming from these other resistors? And it's basically just the voltmeter's resistance is disproportionately high compared to the rest of the circuit. So 3 volts will drop during that period pretty much. It's like some sig figs would be off, but and then here it's in the original circuit, what is the change in voltage across different components? This tests the loop rule, which says that the sum of voltage change is 0. So we know that the battery will go up 3 volts, and then we know that the 2 resistors will go in some way proportional to their resistance and the current. So this can be using Ohm's law and the loop rule, and we get that the battery is plus 3 volts, one resistor is negative 0.975 volts, and the other is negative 2. Now this leaves some room for the resistance in the wires, which we don't know, but those 4 things would sum to 0. Now this is just another way to picture this, where the voltage goes up 3 when it goes through the battery and then slowly dissipates throughout the rest as it goes through these resistors. Okay, now we have a parallel ammeter. So the ammeters have 0 resistance. So in this, there are 2 pathways through the loop, one which goes through 147 ohms of resistance and one which goes through just 47. The electrons are going to go through the lower resistance pathway, and then basically the circuit through that pathway has a total resistance of just 47. Now, because the loop rule still exists and it's still 3 volts, then this one resistor is the only resistance, and then the current will be much higher there and throughout the rest of the circuit. Now we're calculating the resistance of each part of the original circuit. So the 2 ammeters have 0 resistance, and then we use Ohm's law to find resistance is equal to volts over current, and because we found the voltage drop, calculate these by dividing by 20.4 milliamps, and we got 47.7, 98.0, and then the residual resistance we calculated to be 1.1 from other aspects of the circuit like the wires. Now we're testing the charging and discharging time of a circuit with a capacitor and 2 different resistance light bulbs. The lower resistance light bulb led to a much quicker charging and discharging time, and this is because the current is much higher throughout the whole circuit, and thus the capacitor will reach saturation charge much quicker, stopping the charging process and cutting off the circuit. Errors in this were, of course, using a human-timed stopwatch, as well as resistance in the wires, which we calculated, and we only had one ammeter that worked, so we had to move it. If we charged the capacitor with no resistance, it would ideally charge at 0 seconds because there's no resistance in maximum current, but in actuality, this wouldn't happen.